Okay, welcome back everyone. Welcome to this topic 2, which is on a high-low clustering and incremental spatial autocorrelation. I want to summarize last week's lecture and lab a little bit before starting today. Then I'm going to talk about this high-low clustering, which is the Geddes-Ord general G statistic. It's a global statistic. And I'll also talk about how incremental spatial autocorrelation can be very useful in terms of finding the distance in which we're looking at for this high-low clustering. So the main two things to get out of today's lecture and lab exercise are the high-low clustering and how the incremental spatial autocorrelation works with that. All right, so a couple things from last week that I just want to highlight and make sure that we're all on the same page with. And that is, the first is making sure that whenever we're doing any type of spatial statistics, because distance is such an important part of our calculations, it's very important that we choose a projected system of our data, because a projected data has abilities in it mathematically to minimize distortion that occurs when we take something that is on a round earth and project it into something that is flat. So we want to minimize those distortions in shape, area, distance, and then also direction. So we always want to make sure we're using projected data. So the projected data we're using most of the time for West Virginia is in UTMs, Universal Transverse Mercator, but for other parts of the country it might be very different. And even in the Northeast, some of these larger data sets like the one we're going to use today, the Albers equal area conic is a good projection that's often used. So that's what you see as part of this data set for our Appalachian Regional Commission counties we're going to use. So you see at the top, the projected format lets us know that that data is in a projected format. Even though below it might have geographical coordinate system information, you want to look for that projected coordinate system at the top under your layer properties in the source tab. All right, so last time we talked about average nearest neighbor, and we were really only looking at the one question of do spatial characteristics differ? This week we're looking at Geddes-Ord general G statistic, and we're essentially asking additional questions. We're asking if that spatial pattern is changing over time. Are things becoming better or worse for different areas? Certain treatment systems, are they working or not? And the reason why we can ask these additional questions is because we're now able to use an attribute for those points. So again, going back to last week, our average nearest neighbor just used those points by themselves, did not consider any attributes. The Geddes-Ord general G statistic enables us to look at attributes for those points. We're looking at the degree of clustering for either high values or low values. So how do those high values cluster, or how those low values cluster? So this is an example of where we can have low values clustering. So this light purple or pinkish gray color is a feature attribute, the interest we're looking at. So in this case, we see this light purple that's not really clustering that well. There's a low cluster to it as compared to a high clustering of those values that you see here, looking at these polygons. And also, again from last week as a review, here's our average nearest neighbor. Our processing command, as you can see, it just requires the input features, generating report, and we had that area measurement we could put in as a variable. But there's no attributes associated with these points. It's just the points by themselves. Whereas this time in this topic, we're looking at high-low clustering, and then we have another specified input which we require, which is the input field. And that is important with the locations that we have some type of attribute that we're generating from this and calculating the spatial statistics for to determine if things are clustering or not on high values or clustering or not on low values. And I'll talk about these other options we have here. The biggest option with those are the conceptualization of spatial relationships. Really big word, kind of a strange word. What do we mean by conceptualizing our spatial relationships? Well, there's a bunch of different options. There's inverse distance squared, we have this fixed distance band, we have this zone of indifference, k nearest neighbors, and we have this contiguity edges only. So for the most part, what this means is that we have to think about the relationship of, say, for example, polygons and those polygon relationships that are adjacent or in close proximity to other locations. So the inverse distance looks at those neighboring features, and they have a very large influence on the computations. So something like a invasive species spread, that invasive species has to be present for it to spread to other locations. There's a direct linkage between the location and the degree of spread. So that would be a case where we want to use inverse distance. If it was very extreme, we would say inverse distance squared in terms of emphasizing that importance even more. Fixed distance band, that's used a lot in like socioeconomic studies or in data sets that are maybe county, not really county, I should say, more like census tracts, which are smaller in counties, townships, in which there's maybe a neighborhood or a borough designation that corresponds with certain policies, and it's based upon a set size. So in those cases, if you know that distance or size, you can put that fixed distance band in. So an example would be like a zoning ordinance that affects things only within 2 miles. So that fixed distance band of 2 miles could be applied to look at the impacts of neighbors on that particular distance. The zone of indifference is one that kind of incorporates both those aspects of inverse distance weighted and the fixed distance band. And that's the one to use if you don't have any other real driving reason to use these others. The k nearest neighbors and the contiguity, this is specific kind of for neighboring polygons that share a boundary or overlap will influence computations. There's also this scrolls down, there's a couple other ones here related to triangulated polygons or tin values. So they're kind of specific. You can read about those. But the main thing I want you to take away from this conceptualizing spatial relationships, if you're not sure about justification for any of these, go with the zone of indifference, and that's the one we're going to use in the exercise. So this is just them getting a little bit larger, so you can see them outside of that little toolbox. And again, this zone of indifference, this is where we have features at both a critical distance and also a weight influence for those. So this zone of indifference looks like this. These are the other ones in terms of how those distance values are used. So again, inverse distance, here's our fixed distance band, and zone of indifference kind of incorporates these two into this. And this is that triangulation method with looking at neighbors. So the idea in this zone of indifference is that we have this natural effect of distance occurring, changing in values over distance, but we want to know what this threshold is, this point right here and coming down and hitting this. So our goal in using this zone of indifference is to really kind of find this hinge point. And if you remember from, if you had RESM 575 or a spatial analysis class that talked about fuzzy membership functions, we were looking for this fuzzy membership threshold or cutoff or hinge point. And essentially that's what this is. This is a membership function that we're looking for this distance right here in terms of how to apply this. So we're going to use an incremental spatial autocorrelation tool to find that specific distance. And I'll show you that with a demonstration. All right, so once we know the inputs, the field we're going to use, zone of indifference, which we just talked about, we usually use this row standardization. The row standardization is for polygons. So our standardization for rows is the choice we would want to use for polygons. Less important for if you have points or lines, but should be used row standardization for your polygons. And I'll also show you and explain that in a second for in the demonstration. All right, so the data we're going to use in this lab exercise 2 is on the Appalachian Regional Commission. It's a set of counties that define this Appalachian Regional Commission, and there are specific characteristics that they study and look at for this ARC region. And they look for funding, they look for opportunities, business, economic, environmental, recreation, and so on. So it's a really neat study area extent, and it's also interesting in terms of how they're trying to balance the attributes of those areas with opportunities. And so you can read about it more detail if you want on this website. So this is the Appalachian Regional Commission extent. You can see that the state of West Virginia is completely inside of it. It's the only state that's completely inside the Appalachian region. All right, I'm going to jump over now to the demonstration and going through this data. So that's the lecture part of this topic. And the second part of today's video will be a demonstration of the exercise.